Okay, so switching to English now. Welcome, all of you. I'm really happy to see such big response to binary exploitation. I know some of you maybe didn't expect this title because of the Slovenian translation, but I'm still working on that. Okay, first a few words about myself. My name is Aleksander Mundjar. I am a third-year computer science student here at the University of Ljubljani. I am a very big enjoyer of capture the flag competitions. So basically, I don't know if some of you know it or not, but these are security competitions where the idea is to train people who are interested in cybersecurity in a safe way for them and for the organizations they are attacking. My interests mostly lie within boundaries of low-level stuff, so binary exploitation, memory corruption attacks, system security, and I've been dabbing a little bit in malware analysis lately, but just beginnings. Okay. I don't know yet how to call this workshop or course, but the idea of this, let's call it workshop for now, is to familiarize students with the concept of unsecure software. So basically, how does a piece of code become unsecure? So basically, if you have a program, what makes it insecure from perspective of memory corruption attacks? So not misconfigurations and stuff like that, but pure memory corruption point of view. We will go through theory behind some of memory corruption attacks. Here we have a few more coming in, being late. Practical examples of the attacks we're going to cover in theory will be also covered in practice. Most of the programs will be written in C that we'll be exploiting. I always get the question, why? Why C? No particular reason, but the point is not that you're exploiting programs written in C. Binary exploitation and memory corruption attacks cover a vast majority of programming languages, even the more higher level programming languages than C. But the idea with doing it in C is that it's easier to translate between assembly language and C than it is between assembly language and maybe Rust or C++. Those of you who try to disassemble programs compiled in C++ or Rust know how ugly things get really quick. We'll be talking about developing reliable exploits. What that means is that whenever someone decides to publish an exploit on something, generally speaking, in general terms, if the exploit is considered, the more the exploit is reliable, the more it's considered dangerous in some way. What does reliability mean? It means that if you run it 100 times, how many times will it succeed in what it's doing? And of course, all of the presentations and the source code of all the challenges will be publicly accessible. Okay, what is this workshop not about? So, we'll be writing exploits in Python, but this is not a Python tutorial. So, most of you here already know Python quite well. For those of you who don't, exploits won't be complex, and I will walk through every line of every exploit that I will show here. Not a C tutorial, same goes for that. I will be talking about how C translates into assembly language and object code, but I won't be teaching you every dirty detail of C. God help us if I'll be doing that. This is not a course on malware development. Why is this on the list? Well, because what is malware is mostly, not always, malware is basically a binary exploit or a memory corruption bug as a service. That's what malware is. So basically we take an exploit that works on some software, on, I don't know, a browser, let's say a browser, and we wrap it in a nice package so we can ship it to our victims. And this is malware. We will be talking about the process of developing the exploit for the software, not the process of weaponizing it. And this is not a course on secure software development. I will be talking about vulnerabilities and how to prevent them, but not how to write completely secure software, because I don't know how to do that. Additional information that you are currently not aware of is that this is part 1. So basically, to be able to talk about exploitation on a level that interests most of you who are here, who've decided to join us, we have to go through some basics. And these basics cannot be covered in one lecture. That's why I'm planning on having a lot of these, so like 5 for now, every other week. So bi-weekly, basically, maybe next Thursday, maybe 2 Thursdays after that, we will have continuation of today's lecture. Let's call it lecture or workshop. Let's make it interactive. Yes, I want you to ask me questions. I want you to stop me whenever something is not clear. Based on the answers I've collected from the form you had to submit in order to sign up, technical knowledge and skill of people differs a lot in this group. We have people who've just started programming, who have written their first line of Python a week ago, and we have people here who've been programming in Python and C for years. So it's hard to make it interesting for everyone, but whenever you don't understand something or want something to be repeated, please stop me, ask a question, and we will cover it in more detail. Okay, the general overview. This goes for the entire workshop, not just today, for all the upcoming lectures. First, this will mostly be done today. Some of you are thinking, wow, how is he going to cover the whole x86 architecture in one lecture? I'll be cherry picking a lot during this course and using abstraction a lot. So I won't be teaching you how to use something specific and build on that, but I'll try to teach you how to use it in general terms and teach yourself. These words probably mean nothing to most of you, but basically I've listed most of the common attacks based on the attack vector. So stack exploitation, heap exploitation. Basically what it means, stack exploitation stack exploitation easier, of course, everything can be hard if complicated enough. Heap exploitation harder, you need to know more stuff, so that's why we'll probably cover it later in the lectures. Okay, what about the agenda for today? So I'll try to cover a bit about what binary exploitation is, what is the point, then why do people like me do it, and how to get started. We'll talk a little bit about the tools and setup while trying to exploit a program, and we will do an introduction on x86 64. Again, the architecture. It's a very complex architecture and I won't be able to cover everything, but I will try to cover the basics so that you can understand what we are doing. Most of the exploits go and the vulnerabilities work for every architecture. Don't quote me. I don't believe this will happen. I don't have it in slides. So we won't be covering that today probably. Okay, binary exploitation. It says here, I've picked this up from several different sources, but binary exploitation is a process of manipulating memory of the target process, compiled binary, in such a way that benefits us, the attackers. And that's basically what it is. So binary exploitation, or as it's sometimes called, memory corruption, because of attacking memory. But this means probably nothing to most of you. You don't have an idea how it works. So I'll be using a lot of abstraction to try to show it to you. What's the idea, basically? So we have two simple programs here. One has a for loop that counts from 0 to 10. One has a for loop that basically says that counts, doesn't really count, but it counts from 10 to 100 or 99. And both of them have a check just under the loop that says print impossible, string impossible, if count is greater than 10 in this example, and if count is smaller than 10 in that example. Basically, that can never happen. That's why it's impossible. But what would happen if those two processes swapped memory? So, what do I mean by that? Using a lot of abstraction now. If we consider process and its memory as two separate units. That's in practice this is not true, but let's take it into account. And let's say process is executing some instructions, and whenever it needs to basically do anything, or for example check the count variable, it says, hey memory, what is written on the variable count? And the memory says back, it's 5. And the idea of binary exploitation is to take control of this part of the equation and basically say, nah, it's -1. So we want to convince the program that's running that this is the reality. So the memory is something other than the program expects. This is the general idea of what we're trying to do when exploiting a binary and by corrupting its memory. So this slide basically covered what I just said. The what if. Every time we are trying to exploit a process, a program, we ask the question, what if? What if some variable that is set, some variable that should never change, would be something different? What if we control the environment variables? What if we make environment variables larger? What if we can control the connection between different processes, such as attacks, whatever? But we always ask the question, what if? Don't be bound by the construct of one program with a set memory. If you can escape that frame of mind, then you will be very good at this. Okay, why do we do it? To improve security, obviously. The idea is to take an existing software and report vulnerabilities in it, so the hackers cannot exploit them and steal our data. Out of curiosity, basically, you'll see going down the rabbit hole of binary exploitation that it is very interesting, and it's a never-ending cycle of learning new stuff and doubting yourself and not knowing anything. But yeah, some people do it for money. So, of course, if you're able to exploit Chrome browser by redirecting somebody to a page, that's worth millions. Like if you're able to get remote code execution through JavaScript in the Chrome browser, then yes, you can sell it for a lot of money. Fame and glory. Well, you can always be the guy who says, I have the ability to take control of every device on the network that's running this version of software. And then I've exploited this and this browser or this and this kernel or stuff like that from Microsoft, from, I don't know, Google, and be like, I own Google. So fame and glory works in a way that not a lot of people are able to exploit stuff, so the guys who do have very, very big egos as well. And it's very fun. This is the reason I do it, because it's a lot of fun. Unless you're doing it alone, then it's a little less fun, but it's still fun. Okay. How to get get started in it, the story time here will be a little shorter because I have a lot of slides. So how I got started in binary exploitation, that was about 3 years ago. I was playing the CTF competition, the thing I was talking about at the beginning of the presentation. And I was doing it alone. I had no team. So I decided to search for a team within a Discord server that organizers put up for the competition. And I was able to find some guys who decided that they want to accept somebody new. And I was completely new to the CTF story back then. And they said, we need a guy who is good at pawn. This is binary exploitation. I had no idea how it works. But I was like, yeah, I got it. It's easy. I was stuck on the most simple task for about 30 hours. I didn't get it. But, and of course, after that they dropped me. They were like, no, you're no good. We ended up second place, but I didn't do shit. I didn't do anything. So they decided, you're dead weight. We're not gonna keep playing with you. And my ego got very hurt by that statement. So I decided, I'm gonna become very good at binary exploitation, and I'll show them back in a few years that I'm very good. They're still coming up second, I'm still not that good. But it's a thought that counts. Okay. Now for the tools and setup. When I talk about the setup, I mean the setup we're going to be using for attacks on binary. So talking about debuggers, disassemblers, different tools that we use in order to boost our efficiency while dealing with binaries. And if we start with debuggers, it says, let's be honest here, there's only one. Well, I like GDB a lot, so I only use that one, but don't be fooled, there's a lot of debuggers, a lot of good debuggers. But we'll take a look at Inta and Hydra. It doesn't really matter which disassembler you use. Most of them achieve the same thing. Yes, there are some nuances on how they work, how they decompile stuff. They're not completely equal to one another, but for the most part, it's good. Terminal wrapper / emulator. Yes, this is very useful because we will be trying to automate the process of exploit development, which means whenever we run an exploit, we want the process that we're exploiting to start, then a debugger to attach to it, and then we send our payloads and look what happens. So terminal emulator and wrappers are very useful in that. Other tools, I'm going to talk about them later. Okay, so as stated previously, I like GDB. GDB stands for GNU Debugger, and it's basically, it looks like this. It's awful. It's terrible. Nobody likes it. But it's very powerful. It's very good. And if you get used to using it, it's quite a force to be reckoned with. But whenever we find something that's hard to use and annoying, we find the smart people to try to improve that and develop extensions. Extension for GDB is called PwnDBG. GDB DBG gets mixed up a lot. And it looks like that. I have another slide on how exactly it looks just after this one. But as you can see, it's a lot better than this. This is also with all the symbols. This is also with, okay, this binary was created to be debugged. Yeah, this is, but still, it's worse than this. So what I'm trying to say is, this may look horrible, but this is beautiful. Why? Because we're going to the technical stuff now, a little bit. We'll jump right out. But here we have almost every piece of information we want to see while executing an instruction in a debugger. We see the instruction that's being executed, the backtrace of the stack, sorry, the backtrace is down here, the stack, the current values on the stack, the backtrace, so what function we are currently in, what function called our function and function before that, and you know, the backtrace. We have all the registers that are being up there, and then we also have a nice legend, and everything is colored. So if you're not too familiar with address space and you don't know which address this is supposed to be, where's this address located, you can just see it's on the stack because it's orange and stack is orange. So the idea is not to bother using GDB raw without any extensions, to try and get used to this. It's still a lot. It's still going to take a lot of time. It's not easy. But it's pretty rewarding when you're able to master it. Okay, the installation. This is for you when I will publish the slides, so you have everything in one place. You can develop your setup easily. Disassembler. We have a lot of disassemblers. This is not the only one, but these are the two that are the most popular. So we have IDA, that's considered a lot stronger than Ghidra. The other one is Ghidra. But the Ghidra was written by the NSA, so how bad can it be? I personally use Ghidra just because that's what I started with, and because I just like it more. I don't know. I never used IDA, but you can decide on what you prefer to use. It's irrelevant, as it says here. Even object dump will do. Do you know what object dump is? Probably some of you have encountered it. This is the installation process, so it has a package. It's very nice. Terminator. So I've talked before that in order to minimize the time spent waiting and writing instructions and spamming enter over and over again, we try to automate as much as possible. So whenever you're trying to develop an exploit and you're not going to be able to write the entire thing from head without looking at the debuggers, without looking at the memory. Some people do it, but they're pretty good. For that, for my setup, I use Terminator. It's a terminal emulator. It's basically, it's good at splitting windows, and I like that. You can split, you'll see later, you can split windows very, very easily, and I very much like that. I use Tmux for dynamic attaching. We will also take a look at that. Sadly, probably not today, because of the whole x86 architecture thing that we have to go through. But if you don't know what Tmux is, if you don't know what Terminator is, Terminator doesn't really matter, but Tmux is very useful. Okay. Then I said that we're going to develop our exploits in Python. That's harder than it sounds, without that. So basically, 5 years ago, people were writing stuff like sockets in order to communicate with the process, and transforming the endianness and compiling the collecting the addresses, like unpacking them and everything by hand. And this, whenever you're writing it for the first time, it was hell, but then you would just copy paste the script and use it then. Well, instead of copying pasting the script, they developed a library that is used, that has all of the functionality that we're looking for while exploiting already in it. And it's a Python library, so why not use it? The tool PatchElf. Sometimes, if you don't have the source code of the binary you're trying to attack, you know which system library it uses because it's hard coded in the binary, but you either do not have that version of the binary or you want to change it in any way. So The old school way of doing this is opening that binary in a hex editor, finding the bytes that represent the string that is used for the path to load the library, and change it. Well, PatchElf does that for you, basically. And the pawn init, the last one, this is completely a CTF thing. This is completely for competitions. It's basically useful if you want to automate the process of initiating your exploit. So you need some functions that are always present in almost every exploit, and you don't want to copy them or write them all over again every time you're trying to exploit something. This is what pawn init does for you. You can run it, you give it binary, it will read what libraries the binary uses, it will try to download them from the internet for you, and then put a template of a exploit script in your directory. Okay, so now we will be looking at x86. Why? Because I know it best compared to all other architectures. So everything that we'll be talking about is also possible in ARM, RISC-V, MIPS, whatever. Just you gotta know the architecture and its quirks, and then you can adjust whatever you're doing for x86 for every other architecture. Okay, the fun part. Registers. So the registers we'll mostly care about are written over here. So everything else we do not care about, or it's used intermittently. We have stack pointer, instruction pointer, and frame pointer or base pointer. We'll see how all of those are used in a few slides where we'll be talking about how stack works and how the stack frames work. We have a special register for the return value of every function. So whenever we call a function, it will store its return value into RIX register. And one thing I really want to emphasize here, that's why the table is there. Whenever you're looking at disassembled code or reading assembly, a lot of different registers will appear there. So registers like AL, CL, EDI. Lost my, okay. I missed AH.
Yeah.
Alright, so AH is what? Which one?
For byte 1,
Yes.
you have AH. AX is composed of A high and A low, right?
Yes.
So you missed those.
Okay, if we encounter them, I'll mention them, but we won't. So what's the point? Basically, the table does that pretty well, but the point is, if this is R register, so RSP, RIP, RBP, RDI, whatever, the whole thing is referenced. So, oh, this is eight bytes, 64-bit. If we want to say only 32-bit, and we use the E prefix, so like R, DI, EDI. And if we use the EDI prefix, or the E prefix, this is EDI, and so on. So why? Why do we use that? For us, basically this is useful because if you're using a, let's say if you write a program that counts, like we saw at the beginning, that counts from 1 to 100, and you want the variable count to be stored in RDI, let's say, you don't need the entire register because you know it's going to be 100. You only need 1 byte. So you won't be using the entire register. But what difference does that make? Basically, the instructions are smaller if we use AL. So the instruction, I don't know, move AL 10 is smaller, I think 3 bytes, I'm not sure on that, then move RDI 10. but they accomplish the same thing. So this is just a quick intermezzo, basically, to not get confused when encountering. You'll be mostly encountering this E here. That's very common. And in 32 binaries, there's no R. 64-bit registers don't exist. But in 32-bit world, we have EDIs, ECX, EAX, and so on. But they all point to the same register. It's all the same register. That's the thing I want you to keep in mind here. Okay. This was one of the hardest slides to make in this entire presentation. Hex86 instruction set is massive. It's when I tried to scroll through that, I didn't want to do it when I scrolled for a few seconds. But I tried to summarize the most common instructions that get used, and I think these are going to be all the instructions that we will see today. So when we are going to disassemble a program, I'm not sure, but it's 99%. I'm 99% sure that instructions will fall in one of these categories. For those of you who haven't written assembly yet or don't know what exactly it is, yes, I don't know how we're going to continue. But if you have at least an idea of what assembly is and what registers are and so on, then the instructions are basically commented. I commented them, so you know what they mean. The things I want to emphasize are the push and pop instructions. So the push and pop. Now we have push what and pop where. Basically, these are the instructions that are dealing with stack. So it says there stack operations. Whenever we want to put something on top of the stack, we say push and the value. Thing gets pushed on top of the stack. Whenever we want to pop a value off the stack, we say pop and then a register. And the value will be placed off the stack into the register. The branching instructions, it's the same for every architecture. All of the architectures have them. Branching instructions. In this scenario, it's jump. Jump is unconditional. Then if we use the compare or test, we can conditionally branch. And also call and ret are kind of branching because they redirect code execution. So they redirect code execution. That's not whenever one of these instructions is called, not the test, but jump, call, or ret, or one of the family. Jump is one, but then you have jump less than jump more than so on. Code execution is not linear anymore. So basically, you don't instruction 1, 2, 3, 4. If there's a jump here, it's not necessary that you will execute this instruction next. And this is one of the or if it's a call or if it's a ret, it's not necessary that you will execute this instruction next. You will jump somewhere. Of course, you can jump just down, of course, but usually that's not the case. System calls. So this is basically just the instruction for the system calls. Of course, there's some background to this. You cannot just use this instruction randomly, just say syscall and stuff will happen. Registers need to be populated with the right values in order to use the syscall we want, but we will see that later. Subroutines, we will cover this today extensively. So in order to exploit programs with stack-based buffer overflows, we have to know how the stack works. And what this stack mostly used for is subroutines. And the stack is being built and relieved with call, leave, and ret instructions. Okay. So ret, leave, and call. Whenever call is executed, so the instruction call, we are trying to enter a new subroutine. So let's say I'm writing a program that has a main function and then a sum function. The main function is the main function of the program, and the sum function uses two parameters and sums them up, two integers, and returns the result. The call instruction, this has an argument, address. This is the address to the beginning of the function we are calling. So in this case, it's sum. And what happens when we execute instruction call is we need to push the address of the next instruction in the same subroutine onto the stack. Why we do that? Because we'll see the very clear representation of all of this in later slides. But why do we do that is because we want to, whenever the sum function is over, want to return back here. So let's say here's, I don't know, some other instruction, move something, something, Lea, I don't know. And whenever we are finished with the sum instruction, we want to return back. So we use this address to push it. We push this address on the stack for later use. And it can be translated in these two instructions. Basically, it pushes the instruction pointer on the stack. Some of you may think, why RIP, why not plus something? Because if you look carefully, the instruction pointer puts at the beginning. Well, it turns out that's not true. The instruction pointer is incrementing with the instructions. So the call instruction is not only one byte long, it's a few bytes. So whenever the instruction is fully read, only then it can be executed. So whenever this instruction is executed, the instruction pointer is actually pointing here. So that's why we push the instruction pointer, and then we jump to this and start executing our function. Ret first. So basically, ret does this. Ret is this. Whenever sum is over, the ret instruction is at the end of every function, and the returns execution back to where it was called. And the leave instruction does destroys the stack frame and the local variables. Okay. Prologue. Are there any questions? You're awfully quiet. Nothing? All clear? Okay, it's gonna get fun soon. So, whenever we want to, basically everyone who's doing stack exploitation knows these 5 instructions by heart. This is what happens every time we call a function. It's called a function prologue. It is basically the beginning of every function, the setup, if you want to call it. First, so the idea is, what's the idea behind the instructions? If we have a stack, and let's say we are in function main. And then we call sum. So this is the stack for main. And whenever we call another function, we want to give that function space on the stack for its local variables, and mostly local variables, but there's also some other stuff. So what do? On top of stack, we push the base pointer. Then so why we do that? Because currently it's like this. Right, let me just do something. This will be easier. No, not that way. So it's like that. This will be easier to explain with the pictures. So in that scenario, we want to call function 1. So all the way down here, there's a return address to main. So the scenario here is we called function f0 from main. And so we've created a stack frame for function 0, and right beneath it are the addresses to return. So basically, whenever the function is over, we're going to return. Oh, and while at this point, when I say beneath and above, I mean Okay, this is terrible. This is the only right way to do it. I don't care what anyone says. So basically, the stack grows from the higher addresses to lower addresses, and it grows up. The heap grows from lower addresses to higher addresses, and it grows down. This is the image you'll see in debuggers, and this is the only right way to do it. Some people do it the other ways around. It doesn't really matter. You know, whenever if the context is the same, it doesn't matter how we look at an image. But this is what I'm going to be talking about. So if I say something is beneath, it's down. It's actually up, but it's down. So just keep this in mind. So there's the down here, and then we decide to call. So the instruction call gets executed, and we call F1. As soon as we do that, the return address to function 0 gets pushed on the stack, because whenever we finish function 1, we want to return back to function 0. Then we push the base pointer. Why? Because we'll be using the base pointer in the new function to determine the stack frame. So stack frame is always between stack pointer and base pointer. Base pointer or frame pointer, they're used for pointing at the beginning of the frame. Then as soon as we pushed the base pointer on the stack, we can change it. Why? Because we have it saved. So whenever we want to go back, we can just pick it up from the stack. And then we make space for the local variables of the F1 function. And now that we've done that, we've built a stack frame for F1. And both in reverse. Oh yeah, we can put on the arguments. So basically, the arguments we saw in the slide before get put in the Rdi and Rsi registers. This is architecture specific. They get put in some registers usually, and we put them right on the stack. So we have local variables, and the arguments are both on the stack, and they both get referenced by the base pointer. So whenever a program needs one of the arguments, it says base pointer minus some offset. That's my argument. So in the end, this is very important. It's very important if we are going to start the stack exploitation that you understand, that you always have this picture in mind. So it's how the stack frame looks like. And whenever we want to leave the current function and return the stack frame, the word is it gets destroyed, but it doesn't get destroyed. It doesn't get removed. Nothing in memory gets ever deleted. The only way to delete memory is to overwrite it. So the data is still there. Just the pointers are moving around. But the idea is that every function is reusing the stack and putting its local variables in place and doing its own stuff. At the end, so basically when we reach this point, our function is going to execute. It's going to be using the stack, it's changing it, not the pointers, just values on the stack, so local variables and stuff. And when we are ready to return, so when the function is done, we usually see the function epilogue, which is consistent of just 2 instructions. It's a lot simpler than prologue. It basically says leave, that destroys this part, so the local variables, and then it says leave also pops the base pointer, and then it says ret, which basically is the equivalent of pop RIP, which means take a value from the stack, put it in instruction pointer, and move on. So when we look at this like this, first we save the return value if we have one. So if we have the return value, we first write it to the rux register we remember from before. Then the first part of leave, so we destroy the local variables, and now we need to reset the base pointer. So in order to fully return to the previous function, we need to restore its stack frame. So basically what happens as the part 2 of leave is pop base pointer. It pops the value on the stack into base pointer. And now we are back to the original stack frame. We just have to return to the right code segment, basically. You're all awfully quiet. This is not so easy. It seems very easy with all the illustrations and stuff, but this is the basis of stack exploitation, and you need to understand all of this. So I'm gonna wipe the board behind. Are there any questions? When we start what?
You know, if I haven't done this, then I won't understand what you're talking about until I try it myself.
Yeah, but if you want to try it and understand what's going on, you need to hear the theory first. We'll be doing that as well. Okay. Any other questions? All right. So we have a few more slides, 10 more minutes, then we'll have a break, and then it's going to be demos. So we're going to look at some programs and their memory. So whenever a process is being run, it's assigned its memory, so some physical memory and a lot more virtual memory. The resolution of the two is, especially in Linux systems, quite complicated. I didn't figure it out yet. But something somewhere does the resolution of the memory addresses. So basically, the process is its entire virtual, like it's the only process in the computer, and it has all the virtual memory. So 64-bit systems, a lot of Fs are in the end, basically. Yes, now I'll show you some of the segments. This is a view from the debugger. It basically says in the address space of 55555, there are segments from our ELF binary. So in this case, I just took this picture. No, that's actually my picture. Yes, it was from the start binary. We'll see the start binary. It will just be called main. Then we have another mapping. Can you see this actually? Like this will be 7F something. We see another mapping that's mapped for the libraries. So in this case, the library used is libc. And then in the end, there's stack and also the LD binary, the LD library. So we won't be talking about what all of these do, but if you get into advanced techniques of exploiting programs, you will need to know what most, if not all, of these mappings are used, and it's usually not only these. Okay, this is the normal view of the ELF binary segments. This is basically just to get a feeling of how it works. You need to understand it. You don't need to memorize this. God no, don't memorize it. But basically, the interesting one is maybe the only one I'll talk about today is text segment. This is where our code resides. So basically, whenever the program is loaded, the text segment, the address of the text segment describes where our code is. So in this case, where's the text? 5050. Important segments. We will be talking about segments when doing stack exploitation. It won't be in this lecture today because we don't have time. But if you want to do some reading up on your own, by any chance, target one of these segments. They are basically very useful for the attackers. Okay, this is the last slide. We'll see in the demos that everything I just told you, or most of it, is a lie. It's theory. It's how it should be. It's not always like that. And whenever dealing with exploitation or anything in computers, don't assume anything. Prove everything for yourself. Let's say we know that local variables or the local variables are stored on the stack. So let's say I write C, I don't know, this, and this is some kind of function, say sum. We know from theory that it should be on the stack. Why not? It's a local variable. But there's a lot of steps from this into binary or assembly code. There's a lot of loops to jump through before we get there. So if we go into exploitation with this concept in mind, that this variable name, if I could write, is on the stack, might fail miserably, and only figure that out 2 hours in, that we've been actually trying to exploiting something that's not even there. So whenever you think something, you base your whole research or exploit development on that fact, you better be sure it's true. Because I've wasted hours and hours, sometimes days, because I assumed something this isn't true. So if you'll be taking anything out of today's lecture, is that don't trust anyone, not even me, why would you trust me, and prove everything for yourself. Open a debugger, go read the source code. And also this one is interesting. Documentation lies. So it's not intentional. If the developer puts in the documentation what is his perception of what the program is doing, that's not necessarily true. That's how he sees it. So if you ask the developer, you'll say my program is secure. It's impossible to break. But that's been proven wrong time and time again. Abstraction is useful for reasoning. Yes, this whole part I was drawing with memory and with the different arrows and stuff. Whenever you want to imagine, so play the attack in your head with some very complicated concept, you can use abstraction and basically say, let's say that this is true and that is true, and we look at this in that way, then it will work. Okay, conclusion of the first part before we go to demos. Yes. For some of you, there was a lot of new data, and we will see in the demo segment, which will be shorter, that some of it is true, some of it is not. Maybe none of it will work. It's presentations, so they never work. But general understanding is better than I wrote memorization there. Not completely right. Should be targeted knowledge. So as I said in the beginning, exploitation could be taken very generally. So there's no meaning in memorizing every segment and knowing every little detail of how x86 or ELF works. There's no point in that. You can look that up whenever you need it, if you trust the documentation, of course. But I want you to develop general understanding of what the idea of exploitation is and how to then use that understanding to teach yourself how to do it. Okay. As mentioned before, I was throughout this whole presentation, I was talking all the time. When we'll be doing that and this and that. Today we won't be doing any of that. As mentioned before, multiple workshops are planned. This was only the beginning. The basics need to be known. You need to know, or at least be tiny bit familiarized of how the basics work to be able to understand the actual exploit. Because without that knowledge, the house won't stand, so to say. So next time, we'll be talking about stack-based exploitation. So we will do a quick reminder of what we talked about today. So the whole stack frames and building the stack frames and stuff, and then we'll be exploiting them. I've also written some programs for the demos that one of them is very vulnerable, and when you see it, you'll be able to tell me which one it is. They are very simple programs, like the 10 lines, nothing complex. Maybe we'll introduce some advanced stack-based exploitation concepts, possibly. Depends on your feedback. I have a feedback form ready. Depends on how much you learn, if you're even ready to continue with all of this. It gets more interesting, but as I said in the beginning, you can't get to the interesting part if you don't go to the boring basics. Somewhere down the line, we will talk about heap exploitation. Heap exploitation, depending on, again, which system you're attacking, but for the ptmalloc of in libc, so the C standard library, we'll be talking about that. And the heap exploitation is vulnerabilities that arise in software on a daily, not daily, but today in the wild, like it's happening, it's been done a week ago, are mostly on the heap. Why? Because heap is used a lot, that's why. And because stack is pretty well protected. Somebody has to fuck up very hard to allow stack exploitation to achieve something. Okay, so for the next slide, this I'll ask you to scan either now or after the demos better. But now it's coffee break. So it's 7:15 now. Maybe we take 10 minutes off, get some coffee, walk, get some water, and then we'll go into the demos where we will look at the theory in practice, basically. some of examples. I have some examples here ready for you. Basically, they are just some C programs, very short ones, like this. And the idea is that we will look at them in a debugger in GDB, and we will look at the registers, we will look at the instructions, we'll look at what happens when, and the later examples, like example 2 and 3, we'll also see the stack moving, and we will also see the point about not trusting anything, because it won't all work as I described, but it will be close enough. Okay, so in order to which part? No, that's for the people who are watching. Basically, that's my. If I extend the terminal all the way, then some of it gets cut off on the stream. So that's my basically my line where I have to stop.
Tam na projektorju je odrezal.
Oh. Yeah, no. Okay, yeah, thanks. Yeah, tu pa je problem, ja. Okay. So just one moment before we do that, I would like to do this. So what we have here basically is a C program. It's this. It's nothing fancy. And I've ran file on it basically to see what it is. I usually do this whenever examining any type of program. So the file command, if you're familiar with it, I don't know its full reaches and capabilities, but basically it looks at magic values of the file. So basically first few bytes, it decides what type of file it is. Based on that, extracts additional data, it has submodules and stuff like that. A lot of things here will be later on very important to us. But for now, I just wanted you to know that it exists. It's a file command. It's very useful, not just for binary exploitation, but for analysis in general. If you encounter a file that you don't know where it came from, you don't know what it is, this way we see that it's an L binary 64-bit, and then we say, okay, we can run it first. Of course, that never hurts. Prints out hello world. The next thing that's very useful in analyzing it is the Asterisk Command. Here we can follow the system calls that are being called, and because this is a simple binary that only has one puts instruction, so if we boil it down, it's one write instruction. We can see the write instruction right over here, and I think that's a return value 13, the length of the word. I think so, I'm not sure, but in short, it's a syscall, 1 for standard out, hello world, and that's it. And there are also some addresses that you do not have to worry about. Okay, now that we've done that, we can look finally in the GDB. So GDB is, as I've stated, a very complex piece of software. It's a debugger, and basically it is capable of doing almost anything. And the things that the commands that I want to show today are the disassemble command, short for this S. And if you want to disassemble a function, we say this S main. And here we see some instructions being called. Basically, and here we can see the stack initiation I was talking about earlier. So we have the instruction push base pointer, so push RBP. Do you see the instructions? This. So you have from this onwards, have push RBP, then you have move RBP RSP. These two instructions basically create a new stack frame. We don't have the part where the stack frame increases because we have no local variables. We only have one call to puts, and that's it. And after that, we have some other instructions that basically prepare the puts call. And what I want you to see here is the Rdi register. Basically, we said before that in x86-64 we use registers in order to pass parameters to the function or the subroutine. And we can see here that Rdi is used right before the call instruction. And this means that if we, oh, I don't really want to do that. I want to disassemble puts, but that's not a good idea. We will see another example where the instructions get loaded. We'll have another function, and we will see where the arguments get loaded. But here is where they get passed to the function. So the LEA instruction is load effective address. We also had it on the slide. It's not the slides. It's documented there, and it basically says take instruction pointer with some offset and put its reference into the Rdi register. So if we look at how this works, if we put a breakpoint at the start of main and say run, the big fancy screen pulls up that we saw on one of the slides. You don't see the entire thing because of the zoom, but up here are the registers. So this is right at the beginning of main. So we have here the instruction push RBP and then the registers. And we can use NI to skip to the next instruction. And if we skip the first two, so basically now what we've done is executed these two instructions, which should create a new stack frame. Now I will try to I'll try show this to you, but okay, we'll see how this works. I'll say 10gx set RSP. This basically means show me 10 words from RSP, which is stack pointer. So basically show me 10 words on the stack that are on the stack currently. And the G thing is basically it says quad words, so 64-bit. And if I run this, I see a lot of memory. And basically, this is our stack. This is our stack that in this example is not being used, but I just want you to see how it looks like. It's not very pretty. But the idea behind this is that whenever we want to call a new function, the stack pointer will decrease. It will go down because of the memory being the other way around. If we look at this, we see that the memory at the basis of the stack is higher than the memory at the top of the stack. And basically, when we call the instruction sub something from the stack pointer, we are creating a new frame because we are enlarging the stack. Okay, so we'll see this more clearly in our example. Here we have the call instruction, and right before the call instruction, we can look at the registers. So we have call puts, this, and if we look at the Rdi register, it has some value in it. And we see that the extension also looks a bit further. It recognizes this as an address, and it says, okay, at this address, we have a string, hello world. And we can see here that this Rdi is used as an argument, because when I say next instruction, the puts call will get executed, and hello world gets printed out on the standard output. This is not very clearly visible here because of all the other data that's being printed every time. And after that, we have move EAX 0. This is the thing that I was talking about. So it's not RAX 0, because I said in the function, I said integer main. So the signature of the function is integer. Integer is 4 bytes, so we only use the lower half of the register. We don't need to, even though the return value should be written in RAX, here we use EAX, because we don't need to store a lot of data in it. We only need 4 bytes. So we say...
in the higher 4 bytes,
yes.
They just remain there untouched.
Yes.
Okay, but when you read from it, how do
yes.
you know how much you should read? Because you could read the wrong value, actually.
Well, that's a good question. Basically, the question was, how do we treat the register if it's being used somewhere else in the program? Basically, this is the beauty of exploitation and memory management. The higher level programs do that for you. In C, you have to do it yourself. Basically, if you store a value in a memory and you call it an integer, and then read from that memory a long, you will read more data than you've written. So you have to watch out for that. This is good thinking. This is the basis of exploitation. If this would be a program that would say, okay, I've written integer to a memory address, and then somewhere else in the program I treat that as an long, this is an attack that's called type confusion. Basically, you've assumed that at the memory address is a long, so 8 bytes, but actually you've written 4 bytes. And so you've leaked part of the memory. Okay. And in the end, we have the pop RVP and the ret instruction. We will stop briefly in the, no, oh shit. We will stop briefly at the ret instruction and look at the stack again. So we have a ret instruction with an argument. This is not actually an argument, this is what GDB does for us. The instruction is only ret, 1 byte, ret instruction. And at the top of the stack, we have an address. So the 7A03, so on. We can see that that address is what is going to be used as a value for the instruction pointer. And also we can see that the GDB itself recognizes that and says, oh wait, after this return, you will jump to libc start main, which is the function that calls main initially. And this is the example of the return value. Now, one of you asked me during the break, how do we attack stack? How do we attack stack? So how is the stack smashing done? This is the example. So basically, if we were able to override the stack here and set this value to our choosing, then when the ret instruction will be called, we would control the value of where the program jumps. This is the basis of stack exploitation. So there's something on that. But this is basically all for the first example. So to do it again, we basically saw that in main, it's a simple function. We are basically just putting some address in the Rdi register, then calling puts, and the end moving 0 into AX because I said return 0, and popping RBP to restore context, and calling return to return back to libc start main. Are there any questions? Did I go? I'm assuming a lot of stuff. I'm assuming you guys understand this prompt. If anything doesn't make sense, please stop me. If anything of this didn't make sense, stop me also. Because I'm assuming a lot of stuff. I've been told during the break that I assume a lot of stuff, so that I assume that you know the registers, that you know the layout, and stuff like that. I know it's very confusing, it doesn't make a lot of sense, but you can stop me and I will show it again. You can stop me at any time. Okay, so this is it for the first example. Here, we've been doing some testing here. Here we have a little bit of a different program. We have two functions. So basically main and sum. And we can see that we're doing something completely stupid in the sum function. And I would just, assuming that we use a compiler that does 0 optimizations, this will get translated into code that I'm about to show you. If we use optimization in our compiler, this whole program can be summed up to return 0 because it does nothing. But so this might happen to you if you're trying this on your own, trying to write a program and use it to analyze it. If you write a program that is so simple, basically, and does nothing just for the case of showing how it works, you can come in contact with optimization pretty fast, and it will ruin your plans, and you will have no idea why. So basically, whenever you're writing your programs, compile them with O0 flag, which means in GCC, you basically say GCC main.c minus output, I don't know, minus O0. This flag will let you see everything. It's also the default value for the GCC, at least my version. But if it's not, do that. Because I have also an example. We'll look now in the GDB, but I also have the main2. The main2 binary was compiled with all the optimization, and you will see the comparison of the code. So basically, let me just try something. This will be easier. Oh, no, this. If I do this and cat you the code here, will it be easier for you to read? Yeah. Okay. GDB main. Okay. So what we can see here that differs from the first example is that we have the whole function prologue. So we've been talking about this throughout the slides. It's the famous 3 instructions that I said are going to be called at the beginning of every function. In the end, I also said I lied about that part because the 3rd instruction is quite optional, because sometimes the stack frame is not needed. But in this case, it's a good representation of how the stack frame is being built. So basically, these first 3 instructions, if we look at the stack right now. Oh, yes, I have to run the program first. That could help. So if we look at the stack right now, and also look at the registers. So basically, we say stack pointer is it's at DC08, so always the top address. But what we are interested in is the base pointer. So RBP has some, oh yeah, okay. This is a special case. So remember when I said that never trust anything? I was about to say that the base pointer is pointing to the stack. We can see it's not. Why it's not? Because we haven't initialized even the first stack yet. We are only in main. We are at the beginning of main, so basically nothing happened yet. In libc start main, nothing happens as well. We'll look at that some other time, but in libc start main, there's no stack as well. So basically, base pointer was never used in this program. And so we have to skip first few instructions. Okay, I'll stop here. If we now look at the base pointer, we see it's at DC0. And the stack pointer is also at the DC0. Why is that? Because now we've executed the instruction, this one, move RBP RSP, which basically means they're the same. So we've stored the value of RSP, which is the stack pointer, into the pointer. So right now, we have no stack. Stack frame was not initialized yet. But then the next instruction says subtract hex 10, so 16 bytes from RSP. What this will do is move the stack pointer further up, so down the address space, and create us a stack frame. So if we execute this, we will see that RSP now points a little bit lower than RBP does. And if we look at the stack, we see that base pointer is this, and stack pointer is this. And our stack frame in this scenario is this 2 slots, times 8, 16 bytes. This is what happens. Now, right after that, we see that there are two instructions that are using the base pointer, and that are also that are using the base pointer, and these are the assignments. Basically, now we've created space for our local variables, and now we're going to assign them values. The first value we're going to assign is 0xa, which is 10. And so basically what this command does, it basically says dereference base pointer minus some offset. So we move a little bit higher than the base pointer, so here somewhere, and write 10 at that address.
Wait, why are we?
Yeah, it's in the code. I will correct this for the next time. I will correct this for the next presentation we will have. I will optimize this thing so you can have code on one of the projectors and me doing stuff on another, so we can easily follow this. But yes, one of the parameters said int a is 10. That's what just happened here. If we compare the stacks, so here we have an address, and this is the thing you were asking before. Here we have an address, it's 8 bytes. And now we overwrote part of it with our a. And we can see that the other half is still there. You were talking about the other case, so basically when we overwrite the lower few bytes, but the same thing applies. And then right after that, we have another assignment. So we basically, the first part is equal. So dword ptr, this basically means 4 bytes, dereference rbp minus some value, and store f in there, which is 15. We execute this, we see that f got stored in the memory. Now for the fun part. For those of you who are not used to looking at memory, which I assume is most of you, it's little endian plus, which means that it's read backwards. Basically, if you look at this address here, the lower bytes, the least significant bytes are over here, and the most significant bytes are down here. Basically, it's written backwards. This is not really visible here because we have no input. When we will be writing input into the binary, we will see that it's always flipped. That's because of the endianness. And also, offset 0 is here. Offset 4 is here. And now for the fun part, offset, let's say 8 is this. And then offset 12 would be here. And offset 16 is down here. This is how it goes. Basically it goes from right to left and then moves right and zigzag down. That's how the memory is read, if that helps you in any way. Okay, so now that we've loaded the... Now that we've gone, we see this arrow points at the instruction that we were about to execute. Now that we've stored our values onto the stack, our local variables, we are going to load them. So basically, we are first going to load them from memory into registers EDX and AAX. And then we're going to load them from EDX and AAX into EDI, and here is being loaded into EDI. The second is RSI, or in this case, ISI. And we can see here that basically what happens is the local variables are being used as an argument for the sum function. Okay?
Load the variables from the memory to EDX, and then from EDX to ESI. Couldn't it just move it to SI? Or is that the no optimization?
So the question was, why do we have these things here?
Yeah.
That's a good question. I have no idea. So it's possible that because I compiled the thing with 0 optimizations, which means that it's compiling it in the dumbest way possible. But if I used some optimizations, it would compile it in the most efficient way possible, which would be a program would return 0 and nothing else. But the question is valid. So it has a few extra steps which are not needed. But yeah, in the end, it loads the variables into EDI and ECI, and then it will call sum. So now what I want to show is what happens when we call sum. Okay, so we're here. And here, this is what GDB, this extension is also very useful. We can see the relevant registers to the function call. So here the first two registers, RDI and RSI, are set to 10 and 15. And also it shows the RDX and RCX because these registers are used for the third and fourth argument. We are not using them here, but it shows them anyway. So what should we expect to happen when we execute the call instruction? What should we expect to happen with our stack? Does anyone remember from the slides? What happens when we execute call? Yes. So the instruction pointer should be pushed on the stack. Okay. Let me just step into. So I'll use the SI, which is the command for step into. So I'm going to step into the function so we don't skip the whole thing. Okay, so now the call was executed. And if we look at the stack, there's a new value here. I will compare the stacks. So before we called it, it was like this. We had our local variables here and here. And now we execute the instruction call. We still have our local variables. They were just shifted. They're here and here. But now we have a new kid on the block. We have an address. And that address, so 463F, was the next instruction that was going to be executed. So basically an address where the function should return, so where the sum function should return, got pushed onto the stack. See this here. Okay. Now we are at the beginning of the sum function. And I will just disassemble it here. And this is the part where I lied. So what we expect here is that a stack frame is going to be created because we assigned some local variables. If you remember, the sum function said int d and c should be a and b and then return d times d plus c. So we actually defined some local variables. But here you can see that no space for the local variables is created. We don't have the sub instruction. We only have these two. Why is that? I don't know. That's a good question. But it basically still does the same thing. But the important thing I want to show you here is these two instructions. What is this?
Assignment.
Local variables, assignment. So what is the instruction?
It puts the arguments onto the stack.
Exactly. So does everyone see that? Does everyone see why these two instructions are putting arguments to the sum function onto the stack? Now it's the time to say no if you don't. If everybody gets that, I'm very happy.
No.
Great. So basically, when we execute these two instructions, this new stack frame gets created. So let's do that. We're going to execute two instructions. And now we have our new stack frame. So here's our local variable from main, so all the way back. Here is another one. This is the return address. This is what we pushed onto the stack when we executed call. And this is just some random value that was on, sorry, this is the base pointer. This is the old base pointer. We achieved this by executing push RBP. And right now, we are going to execute RBP minus 20, push, so move a value from EDI into address that is in the RBP minus some value. If you look at the RBP, it says this. This is the stack. So at this point, base pointer and stack pointer are both pointing at the top of the stack. And we are going to store values there. Why? Because we need them in the next function, in the body of the function, so what the function is doing. So in the EDI, which is basically RDI, we stored the value of an argument before we entered sum. So before the call instruction, scroll a bit up. No, it's a long way. Here. just before we called a call, I'm just gonna move one further. Just before we executed call, we moved values into ISI in and EDI. And then a few instructions lower, we are using these values and placing them on the stack. Okay, this should make sense by now. So when we execute these two instructions, we've basically placed, we have repeated, if we look at the stack, oh, where are they? Okay, I can't find them. That's not very good. So the old ones are here. I don't see the new ones. Okay, either way, they should be somewhere in the stack. No, they're not. Okay, it's the demo principle, so it doesn't work on demo. But you gotta trust me on this one. Those two instructions actually do that. Was there a question? I think you had a question.
If it moved it onto the stack, why didn't? Yeah, what did it check?
Oh, they're here. Oh, Lord help us. Okay, I have some ideas why this happened, but I'm not sure. Basically, if you actually read what the code does, that helps usually. It is stated here pretty obviously where the variables are being stored, and it's a lot higher up the stack than I looked. Because the stack frame was not the stack frame was not created. The variables are not on the stack. I mean, they are on the stack, but not in the stack frame. They're put a little bit higher, basically. You will encounter optimization and weird stuff all the time. That's why I never assume anything. I just assumed that variables should be on the top of the stack, and they were not. Why were they not? God knows. But they were not. So I should not assume anything. Okay, so there's a lot of register magic that we should basically ignore. The end product is basically some here should be an add instruction. The add instruction will do the adding, so it will sum up the two arguments. The two arguments are because we have no optimizations, the two arguments are passed through the registers, and at the end up in the AX and EDX registers. And in the end, we pop off the base pointer. So let me just move through all of this. So before the add, if we look at the rocks, so AX and EDX, we have our values in there. Basically, it took them off the stack through those weird ass instructions, and it's going to add them up, and the final result should be stored in AX. I'm not sure, but it should be. Yeah. So if we look at the RAX after executing the add command, we see that it's hex 19, which is 25. 10 plus 15 should be 25. So, okay. The interesting part happens right about now in relation to stack frames. We have pop RBP, and then we have return. So basically the two values right now on the stack should be base pointer and the return value. And the base pointer is here. It looks like a stack address. Why? Because this address, and we're on the stack. So this looks like the right base pointer. And then this is the return address that basically, if we disassemble main, should see it somewhere here. It's this one. So it's the address right after the call instruction we executed for the sum function. It's here. And if we execute the pop, we see that the ret instruction will pick up that exact address. So this one, that's on top of the stack. Okay, and if we execute the instruction, we return back to main. Are there any questions? Nothing? Okay. I mean, we're looking at the same thing over and over again right now. So, the example 3, yes, is like this. And I want you to look at the program for a while. And for those guys who know C a little, is there anything off in this program? Okay. So I'll repeat. So what the colleague said is that the printf on line somewhere, there's only one printf. So the printf is not sanitized. What he means by that is that there's no format specifier for the type of variable we are printing. Why is that a problem? Okay, so this is known as a format string vulnerability. We will look at it the next time when we actually start exploiting stuff. It's a vulnerability where if we provide as a name a bunch of specifiers, so %s, %x, %p, printf will interpret them as the first argument, so as the specifiers, not as the thing it should print. And when it will then go searching for the actual string that it should print, not the specifier, nothing will be there. And it will go look on the stack. And with that primitive, we can print values from the stack, and that is known as a leak. So yes, that is the first thing. There's another thing wrong there. There's another problem. Exactly. So to repeat what the colleague said, we have no way of knowing what the length of the string we read is going to be, because if you look at the scanf source code, %s means everything. Means read until you reach a white space character or an actual space or a new line. So basically, if we just put 200 A's as a string, that shouldn't be a problem by the program. Now, some creative thinking. What will happen? Why is that bad? While I start up the GDB. Okay, that's true. Okay, I'm just gonna try something first. So we're gonna print a lot of A's. So screaming at binaries is common here while testing them. What happened here? That's what it says. Great. I want to know, okay, if somebody can tell me what is this and why this got triggered, I will buy him a coffee. Ti ne šteješ.
Practically destroyed the data where it should return, so it doesn't know where the program is, which program actually ran.
Okay, but okay, this is but the program didn't fail. The program got aborted. Yes, we overflow what? Okay, what's on the stack that we care about? The arguments are on the stack, but the arguments are not, how should I say, vital to the execution of the program. Exactly. There's the return address on the stack. there's a return address on the stack, and we overflew, is that a word? I guess. Exactly. We overflown the stack address. That didn't sound right. But the stack didn't segfault. The program didn't segfault. The program aborted. So what happened? A system call exit was called. You're not supposed to know this. I'm just interested if somebody is already dabbled in exploitation a bit and not. Okay, we're. Yes. So basically what happened here, the stack got, we've overflown the stack, but we've overflown the return address, sure. But there's something on the stack that prevents us from exploiting buffer overflow vulnerabilities. It's called a stack canary. We will get familiarized with protection techniques involved in binaries the next time we have the workshop, and one of them is stack canary, or stack cookie is also called. Basically, every time the function returns, the canary is checked. If the canary changed, that means we've overflown the buffer, and so the program exits automatically. It does not return. This is why this is printed. What about this? Come on, UV. Why is this unknown? Oh, he should know that. Great. So we didn't overwrite the name per se, but we overwrote the pointer to the name. So basically, at the bottom of the stack, we didn't tell this, but at the bottom of the stack there are environment variables. And in the environment variables, there's also a name of the program that's currently being run. And what should have happened here, this should have said main terminated, because the name of the program is main. But as we've written so many A's, we didn't just overflow the stack. I mean, just our stack and a few variables lower. We overflown everything. So we've also we also smashed the environment variables, and everything breaks at that point.
Okay, but don't just check.
Yeah, it's pointing to a very interesting address. I'll just stand up for a moment. It's pointing to a very interesting address.
But there is something.
Yes, there is. But when we talked about resolution of virtual to physical memory, the process only thinks it has all of the memory mapped. When this thing goes up the food chain to the kernel and tries to resolve to an actual memory, it's pointing nowhere. So not every bit of memory, of virtual memory, is actually mapped. Just the process thinks that. Or it's in a sandbox in a way. So yeah, we've overflown the pointer, and so this makes no sense to the binary, and then that's why it says I'm not gonna bother. It's just unknown. Okay, so great. We figured out that. We'll be talking a lot about canaries and about other protections next time around. I just wanted for the last time to show this function real quick. And I have two questions for you. First of them is, what's up with this? What should be there and why is it not there? Or maybe it is. Let's go with the first one. What should be written there instead of this? Subtract, yes. there should be a subtract RSP something call to create the stack frame. What is this? Yes. This is basically the same thing. This translates to subtract hex A, I think, or I don't know. I don't do math. I have other people who calculate for me. But this is a negative number. Yes, it's a if it's treated as a positive number, it's a very large number. But if it's treated as a negative number, which it should be, it's negative something, negative around negative 100, 120, something like that. Okay, this, what is this? Should already know what this is by now. Arguments, great. And where are they being placed? Is this near the stack pointer or far away from the stack pointer? So which is it now? Is it near the stack pointer or far away from the stack pointer? What I want to test now, if you have this image in mind. That should help. Between the stack pointer and the base pointer, there's a stack frame. And this says, subtract some hex value from base pointer and write there. So is it closer to base pointer or the stack pointer? Base or stack? It's closer to the stack pointer. Why? Because if we subtract from base pointer, we are getting closer and closer to the stack pointer. If we
don't know what stack pointer is, so if you knew, you could like literally
we know what the stack pointer is.
Wow. It's RBP minus
no, we'll just look.
Yeah, okay, sure. Yeah.
Okay.
No,
so we see one more thing that happened here. We will just look. Okay. We have a stack pointer right here. And the base pointer is right above it. I can also print the stack. Say stacks. No, I won't do that because stack's quite large. And it will fill up the entire screen. Okay, so what can we see here? If we look at the first three instructions, so the push, the move, and the add, that did what? Okay, without the, just the first three, just the first three. Exactly. So that created the stack frame. So right about now, we have a stack frame of the size, how much? Hex 80, exactly. Okay, and then we are trying to write at base pointer minus hex 74. So is that close to stack pointer or close to the base pointer? Close to stack pointer, exactly. It's 12 bytes higher than the stack pointer, and it's obviously 74 lower than the base pointer. Okay, does anyone know why is that the case? Why didn't the compiler just write it close to the base pointer, so at the bottom of the stack? Why did he write all the way up there? Now I can even show the stack. Should I even do that? That's a good question.
More space to overflow.
It does have to do something with overflowing stuff, yes. We have base pointer page. Okay, so this is our stack frame. Why did the program put arguments at the top? So I think they're gonna be here and here, I'm not sure. But somewhere close to the top. Why are they not close to the bottom? Yeah, but the only thing that changes is the value. So we don't gain much by that. Well, whenever I'm trying to explain this part, I tell a joke. Whenever there's a room of people, and it's not really a joke, it's an observation that's always true. Whenever there's a room of people and you find the smartest guy in the room, GCC is always smarter. So why is this the case? Because GCC knows that we have a buffer on the stack, and it wants to put the buffer as close to the stack canary as possible. Oh shit. Why? Why it wants to do that? Because it doesn't want us overflowing other stack values. So sometimes when you have a buffer overflow, it doesn't mean you have to attack the return address. There could be other values on the stack that are used in the program that could maybe allow you to manipulate the program. So the GCC says, okay, there's 4 integers and there's a buffer. We are going to put the buffer at the bottom of the stack. So if we overflow, we are going to hit the canary immediately. So a better canary is, sorry for moving so much, guys. The canary is here. Sorry, here. Red can. So the GCC will put the buffer right next to the canary. So if we overflow, we will hit first canary and nothing else. So it's not possible for us to overflow anything. We will just hit the canary and program will crash or exit. We load the registers. Okay, yes. This is one of the commands that I was trying to avoid, but I forgot to put a compile flag while compile the program. This is the canary. Or we can take a look at the canary. Basically, this places the canary, okay, no, actually, this places canary onto the stack. We can very easily find the canary. Canary is here. So this is the canary. This value is going to be checked every time we exit a function. So basically what GCC does, it takes our function, it prepends the prologue, so the things that creates the stack, and it appends the epilogue, which is the ret leave. And if we compile it with this protection, it also prepends at the end check for the canary.
So you actually know exactly where the canary is.
That's relative. That's relative. You know exactly where the canary is relative to the base pointer. Yes. You don't know exactly at which memory address it is. Okay, you know it's on the stack, and you know it's exactly above base pointer. So base pointer is this. This is the base pointer. And here is the return address. And this is the canary. This is, yes? Yes. So the question was, could you somehow bypass the canary? Was the question. So yes, the technique to bypass the canary is first you have to know the canary to be able to do that. But if you are able to leak the canary, like for example with format string vulnerability we saw earlier, yes, you could just overflow right to about here and then say, oh, I'm just gonna leave this value as it is, so I'm just gonna write these exact same bytes at this exact same position and then just keep smashing the stack. Yes, that's possible. Okay, here you have the scanf. Scanf asks us for some input. I will be not so generous. Okay. Find my input. Exactly. Find the arguments. Find the arguments to the sum function. Where are they? Remember what we said before about buffers and variables. Do you think, are they below the buffer or above the buffer? So, where are they? Exactly, here. So you can see that the buffer started here. This is our buffer. and it goes all the way down to here, to the canary, but other arguments are above the buffer. That is to prevent buffer overflows to have additional reach or harming potential, if you want to call it that. Okay, then we have printf. Aha, the bad printf. You see the problem here. It says here, format. In this case, the format is our A's. If this weren't A's, if this was a % something, fun stuff would start to happen. The other argument is just random. We don't know what it is. We didn't set it. So it's just, I think it's just top of the stack, but I'm not sure. Printfs are weird. Then we have puts that just prints nothing. And at the end, leave and return. Okay, just before we end, I want to show you what happens in here when we smash the stack, when we overflow the stack. I didn't need to do that, but break at some run. So we want to break here. Okay, so we're at the scanf right now. And before, I was not very generous with the input. I just put a few values there. Now we're going to look at the stack before the overflow. Stack looks like this. It's exactly the same as before. And our buffer starts here. But now we will overflow the stack. We'll overflow everything. I'll say next instruction, and I will hold A for a while. This should do it. Okay. Now the stack looks like this. Where is the return address? How do we find the return address? Yes, look at the base pointer. Base pointer is here. So db_e0, base pointer is here. Where is the return address? So is it this one or this one? Okay, it's this one. So base pointer is always pointing to the previous base pointer. So we've actually overflown the previous function's base pointer here. We overflown the return address here, and we've overflowed the stack canary here. And now what will happen if I continue the execution? I'll try to find the call to the puts. It's relevant. I'll try to find the XOR. Okay, here's an XOR call that basically says XOR the variable at fs some offset. Fs is the internal register. We will talk about it as the usual. We will talk about it later. But here's a canary. Fs and some offset. This is where the original canary is stored. So this XOR XORs the values. And then it will check if the result is 0. If the result is 0, we can continue. If it's not, something else will happen. Okay, we've XORed the values, and XOR should be stored at RCX. RCX is definitely not 0. It's some gibberish. And it will say jump equal. So if it's equal to 0, the RCX, it will jump to here, which is just continuing the execution in main. Otherwise, it will jump to a function that's called stack check fail. And because we didn't, so I can just step into, because we didn't succeed in the stack check, we ended up in the stack check fail, which through a lot of wrappers calls stack check fail, which then aborts the program. This is what is happening under the hood. But we will see that canaries can be beat. They have been beat before. And what's most important, even this value, so this is the previous base pointer, this or this are both targets for buffer overflow. We will talk about them next time. of course. So this is all from my part. Questions? Are there any questions? We've been quite long. Depends. Oh, yes. Just one thing before we go. I want to. Oh shit, that ain't good. Come on. Magdu podatke. Thanks. I'm basically trying to show you the feedback form. Ne, zdaj bom sam se konektal. Ne?
Tečaj. Miga?
Kaj imaš? Na, kar napiš.
Tecaj.
I just want you to... Come on. Yeah. Always scan the hacker's QR code. Okay, try it now. I won't maximize the output. Basically, when will the next time be? Either a week from now or 2 weeks from now. I hope for a week from now. And I hope for at least some of you to come back. Basically, some people already left, so they won't have this. But this is basically a feedback form for today. There was basically a plethora of skill sets. Here, people from who've just started programming, people from master's programs. So it was really hard to adjust. But moving forward, I would like to hear your guys' feedback and what do you think went wrong, what do you think was good, and this is what this form is for. And at the end, there's an invite to a Discord server where we'll be able to communicate easily. I will also make PR announcements as for today, so there will be announcements on the monitors in Aula, and also you will get notifications from what's that called, Informator. But this is just easier. For the next time, we will dive into stack exploitation, so we will look into techniques used to prevent stack exploitation and how we actually do it. We will have practice problems. Tell me in the form if you want to do a basically work along where I'm doing stuff and you guys are actually working with me. So we will rather than be in one of the lecture halls, we will be in the computer room where you will have access to computers, or bring your own laptops, I don't care, and work along with me. Or is this better for you? Just tell me whatever. Tell me whatever you thought of the presentation. Should it be longer, shorter, more slides, more demo, less slides, stuff like that. Other than that, this is it from my side.